Welcome to Mrs. Miller's notes for her pre-calculus class. These are the notes for section 6.1, day 2, entitled Angle Measures. And today we're just going to talk about two more concepts. We're going to talk about the area of a circular sector, and then we're going to talk about circular motion formulas. Now, yesterday we talked about the arc length. So we talked about the length of an arc as you go around a circle from your initial side to your terminal side of your angle measure. But now we're going to find the area inside that space. So the area of a sector is, if you have your initial side and then your terminal side, okay, this outside piece here, that's your arc length. The area of the whole sector now will be the area of this whole inside slice. So it's like the whole piece of pizza or pie. And it's based on this formula. The area of the sector is 1/2 times the radius squared times the angle in radians. Okay, and that angle is going to be the central angle. So that central angle is going to be the angle that's inside that shaded area, the angle that you're traveling to go from the initial side to the terminal side. Okay, so your problems to practice this concept will look like this. Find the area of a sector of a circle with a central angle of 60 degrees and a radius of 3 meters. Now the thing is, for this one, they gave you the angle in degrees. And if we're using our formula, we don't want the angle in degrees. We want it in radians. Okay, theta was the angle in radians. So you either have to know or you have to convert 60 degrees to radians. Now if you know your unit circle, you should know that 60 degrees is pi over 3. If you can't remember that, then multiply it by pi over 180. Remember, we are converting it to radians, so we want the pi in the numerator, and then that will reduce down to pi over 3. Okay, so we need to do that little side work first, and then we can take 1/2 times our radius was 3 squared times the pi over 3. Okay, so there's a couple different ways that you can simplify this. Hopefully you see that we'll have a 3 and a 3 that will cancel. But if we just multiply across the numerator here, we'll have 9 pi, and then the denominator would be 6. And then 9 over 6 we can reduce to 3 pi over 2. And that would be meters squared for the area. And you've dealt with this before in geometry. In geometry, it was a proportion, and you were dealing with the degree measurement instead of the radian measurement. So this is just a step up from what you saw before in geometry. Okay, now we're going to talk about circular motion, and there's two ways that we can measure circular motion. We can describe the motion of the linear speed or the angular speed. That's how we can describe the motion of the point. Now, linear speed is the rate at which the distance traveled is changing. So this distance here, this arc length, so the linear speed is the distance traveled divided by the time. Okay, so linear speed is that arc length divided by time. And we can also measure angular speed. Angular speed is the rate at which the central angle is changing. So that's going to be the number of radians divided by the time. So in both cases, we're dividing by time. So linear speed is going to be represented by a little v, and then we'll have s over t. Now remember, this s, that's the arc length that we were talking about in the previous section of notes. So that's the radius times theta, or our revolutions. The angular speed is going to be represented by this little w, and then we'll have theta over t. And again, this theta, that's our central angle in radians over time. So these equations are somewhat new, but they relate to what we saw yesterday in the previous section of notes, and they relate to each other, as we'll see in a moment as well. Okay, so for example 6 here, they want us to find the linear speed and the angular speed for this situation. And we have a boy that rotates a stone in a 3-foot-long sling at a rate of 15 revolutions per second. Oh, I'm sorry, per 10 seconds. So we're going to find the angular speed, and then we're going to find the linear speed of the stone. So we want to know how fast that stone is going. Okay, so if we're going to find our angular speed, that was our equation with the little w. So we have theta over t. So again, theta has to be our angle measure in radians. And we know that our time is going to be every 10 seconds. Okay. And to find the radian measure of our angle, we know that the boy rotated the sling around 15 revolutions. So he went around in a circle 15 times. And to go around a circle, that's 2 pi. And he did it 15 times. So that's how big his angle measurement was. So he started with 1 revolution and just kept going constantly 15 times around the circle. Okay, so that's going to be 15 times 2 is 30 pi over 10. So that would be 3 pi. And that would be radians per second. Okay, so that means he went 1.5 times around the unit circle every second. That's how fast that stone was going. And then the linear speed then is going to use our other equation, v equals s over t. Now remember, s is really our radius times the angle. Okay, that's our arc length. S is our arc length. So now our time is still going to be 10 seconds. And our theta that we found before is still going to be the 15 times the 2 pi. So the only difference is we're multiplying our radius in there now as well. So really, angular speed is the same as the linear speed. You just multiply it by your radius. So then we'll end up with, let's see, 30 times 3 is going to be 90 pi over 10. So that reduces to 9 pi. And our radius now is feet, so this would be feet per second. Okay, so that's how fast the stone was moving around the outside of the circle. So angular, that's how fast the angle is changing. So the angle, we were moving basically 1.5 times around 3 pi. We were moving 3 pi per second, or 1.5 times around the unit circle per second. And this is the distance then for that measurement. So basically, if you take 3 pi times 3, you get 9 pi. Okay, so that connection between those two linear and angular speed formulas is right here. If we take our angular speed, the w, and multiply it by our radius, we get our linear speed. Okay, so the linear is equal to the radius times the angular. That's basically the connection between those two formulas. Okay, so let's take a look at one more example here. Here we have a woman who's riding a bicycle, and the wheels on the bike are 26 inches in diameter. So I'm going to stop and I'm going to draw a little circle here. There's our bike wheel, and we have 26 inches in our diameter. So that means our radius is 13 inches. Okay, we might need that. If the wheels rotate 125 revolutions per minute, find the speed at which she is traveling. Okay, now this speed, the speed at which you're traveling on a bike, that would be linear. Okay, so they want us to find the linear speed. Now, the linear speed was V equals R times W. Okay, if we took our angular speed and multiplied it by the radius, then we got our linear speed. So we're going to then take our radius, which is going to be 13. They tell us our radius, so it was good that we wrote that down. And remember, the formula for W, I can rewrite this up here, is really the theta over t. So I need to know my angle in radians, and I need to know my time. Okay? Now this is where the revolutions per minute comes in, because my time is going to be 1 minute, and then I'm going to do 125 revolutions. So that's 125 times around this circle. And remember, you go around a circle once and you've gone a distance of 2 pi. Okay? So this will be my linear distance then. It will be 3,250 pi. Let me multiply that out. Now you could write it like that, or if you wanted to multiply the pi, you could have 10,210.18. But either way, this is inches per minute is what we found, because we had a radius of 13 inches and our time was per minute. Okay? They don't want that though. They want to know how fast she's going in miles per hour. So we have to do a little converting. Okay? So it doesn't matter which measurement you start with. You could start with the 3250 pi, or you could do the 10,210.18 inches. Okay? Either way though, whichever one you start with, we have to convert. Now these are both in inches. Okay? So it's inches per minute. So we're going to have to change those inches into feet. So we're going to have to multiply by 1 foot over 12 inches. And then I'm going to have to multiply the feet into miles. So in 1 mile, there's 5,280 feet. So now my feet have canceled. My inches will cancel out because these were both in inches originally. This was inches per minute. So was this one, inches per minute. Okay, so now the inches has canceled. So now we've got it in miles, but we still have it in minutes. So now I've got to multiply by 60 minutes in 1 hour so that I can cancel out the minutes. Okay, so then your answer, if you were using pi, you would take the 3250 times 60, and then you would divide it by whatever 12 times 5280 is. Reduce that all the way down, and you get 1625 pi over 528. And that would be miles per hour. Or if you were doing your decimal here, you would take your decimal, multiply it by 60, and then divide by 12 times 5280, and then you would get 9.67 miles per hour. So either one of these would be an acceptable answer. Probably makes a little bit more sense for us to write it as the decimal, 9.67 miles per hour, just because that's how we speak about speed. We don't measure it in pi when we're just speaking about how fast we're traveling. Okay? So these formulas can be a little tricky, just remembering what information goes into what variables location in the formula. So definitely have those written down. Maybe have the charts in the book handy as you're going through these practice problems. Remember, they're all odd, so you can check your answers in the back of the book, and then come on and see me before school if you have questions.